All right, so let me introduce myself. If you don't already know, I am Dan Rein, the chemist here at Jonas Chemicals, and this is the fourth educational webinar I've done for this summer, in a series of total of four that I've done this summer on different topics. So the topic for this one is swimming pool water balance, chemistry, chemical factors that make up the water balance, otherwise known as water chemistry. So there's a ton of information out there online or in lots of different places about swimming pool water chemistry. A lot of you probably know it, a lot about it already, but my goal with this and the other webinars is to present things in a way to show you guys how what my perspective is as a chemist and a scientist, how I look at these things, and hopefully you guys can get something out of that too. So let's go ahead and get started. So there's three groups that we can group pool and spa water quality into these three groups that affect water quality. So biological factors, that has to do with any living things, chlorine, sanitation, oxidation, and any algae or bacteria or living things, and how that the effect on this of those things on the water. Then you have physical factors, which is the circulation and filtration, particles, any particles in the water, physical particles, and physical filtration, like your filter system and your pump, which circulates the water around in the pool. And then the third one is chemical factors, which is what I'm here to talk about today. So anything having to do with water balance that's not chlorine, pretty much. The main things are the pH, alkalinity, and hardness, and any other factors like any metals in the water, CYA level, or TDS, which is total dissolved solids. Okay, so here they are again. TDS is total dissolved solid. CYA is just short for cyanuric acid. So sometimes we use one or the other interchangeably. It means the same thing. And then any minerals in the water is technically part of the water balance. So, but the important thing, probably the most important thing, is the pH that I look at. Alkalinity and hardness, and also CYA is pretty important too. So let's get into what each of these are and how they relate to the water water balance. So for pH, the industry standard is to keep the pH in the pool or spa between 7.2 and 7.8. So pH affects the killing power of chlorine. Actually, it does. Actually, in the presence of CYA, which pretty much all pools have some level of cyanuric acid, the killing power is not affected by pH. From what I've read in some studies, without CYA in the water, yes, more acidic the pH, the more killing power the chlorine has, like a lot more. But when there's CYA present, that's not the main thing that determines the killing power. The main thing is the level of chlorine, ppms of chlorine. So even with CYA in the water at pH 7.2 or 7.8, the killing power is pretty similar. The main difference would be if you had, or if you're at 1 ppm, it is pretty similar. So if you had in one pool had 1 ppm, one pool had 2 ppms, the 2 ppms pool would be about twice as much. But pH doesn't have too much of an effect. I think people probably a lot of people still think that it does, because when the industry started, they weren't using cyanuric acid, they were adding chlorine every day. So probably in the initial studies that they did, they realized in the initial studies that pH had an effect. But when other studies were done later on, when pools were dosed with cyanuric acid levels, the kill rates were pretty similar at different pHs. I think I have a slide on that on a little later, but I should talk about it now since it's right here. So the main thing about the pH, though, why it's important in the pool water, I guess, is that the lower the pH makes the water more acidic, and acidic water generally is more corrosive. So you don't want corrosive water touching any metal parts, especially if you have heaters and things like that. But also with plaster and liners, no matter what your pool is, corrosive water over time will eat it away and break it down. So the more corrosive the water is, the faster your equipment and surfaces will degrade. So that's with a lower pH. With a high pH, if the water is alkaline, it tends to precipitate things more, such as calcium, which is also part of the water balance, is a calcium level. So most of the times, the reason for scaling, and which is a precipitated form of calcium carbonate, usually the reason for that's usually not because there's too much calcium in the water. You can have a pretty high level of calcium in the water. The reason is that the overall balance is high. So you can have a high calcium level and still have a balanced pH. Maybe if you just maintain the pH level a little bit lower, it still can be balanced, which I'll talk about later. But that's generally how it works. So if we want to measure pH, there's a lot of different ways to do it. Fastest way is test strips. I have a picture of the test strips that I use in the lab. Goes all the way from 0 to 14 range. So they're not really accurate for pools. Most pools are between or somewhere in the 7 range. So they're good to get a general idea. The pool test strips obviously have better accuracy, but they're still pretty hard to read because the indicators, the colors are like a light. It's either like a light or a dark color, and sometimes it's hard to tell with great accuracy. So another thing people use that's real accurate is the pH to drop test with the phenol red indicator, and that'll give you a good accurate pH reading. But the thing that I like best for measuring pH is a pH pen, which is something like the picture that you can see. It gives you it reads the temperature of the water, and it actually takes that temperature into consideration when it's calculating pH. So it changes at higher temperature, so it needs to consider that to accurately measure pH. It's very accurate as long as it's calibrated and maintained properly. So that even an inexpensive pH pen has less than 100. You can get them for less than $100. We sell them as well. They're very accurate and fast. You just dip it in, read the pH after a few seconds, gives you an accurate reading, and I can rinse it off. And like sometimes with the colorimetric or the drop test, if you have a high chlorine reading, or if you have even any kind of chlorine level in the pool, it can bleach it out and cause the pH to read a little bit lower than it actually is. So these pens are not affected by the chlorine levels that are in pools. like some other methods can be. Test strips too, they can get bleached out and the pH will read a little bit lower than it actually is. Yeah, so okay, I started talking about the before you can have a high calcium level and still have balanced water. um, if you base your calculation on the LSI, the Langley saturation index, which is the best way if you don't mind going the extra step to do that calculation and find out whether your water is corrosive or not. It's and so I'll talk about more about how the LSI calculation works at the end, but that is the best way to balance the water. It takes all these factors into consideration instead of the traditional way, which is just to use targets like in general, the targets for a swimming pool is like 7.5 pH, 200 calcium, and 100 alkalinity, right? That's the most simple way to balance a pool, is just to hit those targets. But you can't always hit them exactly. And so it's good to do the LSI calculation sometimes to get a better idea of what's actually going on in the water. Yeah. So, and I know it's a little bit, a little bit lower for saltwater pools, that the alkalinity and the targets could vary a little bit, but they're close enough to me that you can use those targets for everything, just to keep it simple. And if you do LSI calculation, that should be a very good give you a very good idea. So for alkalinity, we target 100 alkalinity. You want it to be at least like 80 ppms, and somewhere between 80 and 120 is like a good range. So the purpose of the alkalinity, the main thing it does is it buffers the pH from going down. So like instead of say if you add something acidic to the water, or acidic rain falls in the pool, causes the pH to go down. Whatever it is, when that's added, a reaction happens, the pH goes down. So when you add alkalinity to the water, when you have that about 100 ppms alkalinity, the reaction eats up the alkalinity instead of causing the pH to go down. So it's sort of like a storage, like a buffer, to help you maintain that pH in that good range. And it also contributes to the LSI, and makes your water less corrosive. And so you'll see how that fits in towards the end with that too. So the chemicals that we use to raise alkalinity in the water are the alkalinity is actually sodium bicarbonate, which is baking soda, will raise alkalinity. The soda ash, which is as you can see, they're pretty chemically similar. The soda ash is used as pH up because it's like a stronger version of the same thing, carbonate type of a chemical too. It's got that CO3 on the end, which is what gets stored in the water, and it's actually called carbonate alkalinity. So you have your carbonate alkalinity, which you can add. Adding either sodium bicarbonate or soda ash will increase your pH and your alkalinity, to some extent. If you want to just increase alkalinity, the bicarbonate's better, so it won't raise your pH too much. Or if your pH is too low, use the soda ash, the pH up, to get it up faster, and then you can always add more after you test your water and see where they end up. So these things you can add a little bit at a time, then test your water, and you can sort of get a feeling for how much they'll increase your alkalinity and your pH. these don't have to be exact. As long as you have, around the target, it's good. It'll keep you pool water quality balanced. So it's actually probably better to be a little bit higher on the pH and alkalinity side to prevent your water from being too corrosive. I'd rather have water that's a little bit has a scaling tendency, because that can always be corrected. But if your water slips into the corrosive area, over a period of time, depending on how corrosive and how much time passes, that can cause major problems. So the two types of alkalinity we talk about are carbonate alkalinity, which is the type that gets added through these chemicals, these carbonate group chemicals, soda ash or bicarbonate, and so that should be the bulk of your alkalinity measurement. But the cyanuric acid also has a buffering effect, which could be good or bad, depending on how you look at it. But when you measure alkalinity, most of the tests, they measure total alkalinity. So the way that you can find out how much of that is from CYA and how much is from carbonate is that the carbonate is equal to the total minus 1/3 of whatever your CYA measurement is. So that'll give you an idea as how much is from the carbonate, how much is from CYA. But as long as the total alkalinity is within that range, it still counts as alkalinity, because it still has that buffering effect that is the main purpose. So calcium is also related to the pH and alkalinity and water balance, in that the carbonates get stored in the water as calcium carbonate compounds. So there's this reaction that goes on, this cycle between the different compounds and reactions going on in the water. Calcium level should be at least 200, between 200 and 300 at least. You actually can have much higher calcium levels, but there's not a reason to, as long as it's balanced with around 200 to 300. So as long as the LSI is in range, you can have high calcium levels, and it shouldn't really hurt. You shouldn't have scaling problems, as long as the water LSI is in the appropriate range and not too far on the scaling side of the index. So this is goes along with everything else we've been talking about with corrosion and scaling tendency of your water. So adding hardness to your water, calcium hardness will increase the LSI. It'll decrease the corrosivity of the water, because it'll push the LSI index number up higher. So it's important with even with vinyl pools or with plaster pools. You need to have some calcium in the water, because plaster, especially plaster, is made from calcium. It has these calcium ions in it. So things always tend to want to come to equilibrium. So if you have calcium in your plaster wall and no calcium in your pool, the calcium tends to want to go from the high concentration to the low concentration, from the wall into the pool, which you don't want, because you're leaching, the structural metals from your pool wall, which is not good, right? So you need to add that calcium level. You need to keep that calcium level up, and so there's a calcium level in the wall and in the pool, so it stays in equilibrium, and there's no transfer of calcium ions, no leaching from the calcified walls of a plaster pool. And similar, even like I said, it's important in vinyl pools, because the corrosive water can break down the gel coats and make them wear out much faster than they would otherwise. Like I mentioned, one problem people have is scaling, like a white scale material that's a calcium carbonate, usually type of a scaling on the walls or on heaters. By the way, the reason calcium forms on heaters is is like most compounds usually most compounds precipitate out of water when it gets cold, like ice turn or iced water turns to ice when it's very cold. But calcium, for whatever reason, is oddball. So calcium tends to come out of solution in warmer in a warmer environment, actually. So it actually turns to solid in the warmer temperature. The warmer you get, the more solid calcium you end up with, which is why it tends to precipitate on the hot, the heating elements in the of the heaters, pool heaters. So one thing that if you do have a heater, especially, or even if not, sometimes it's good to use a sequestering agent like Ketrol is a great one for preventing this type of calcium scaling. It's a chelator sequestering. It forms like a bubble, bonds to the metals, and it sort of keeps them invisible, keeps them in solution in the water, and kind of holds them in solution so they don't come out of solution so easily. And it's a good one. It's used, Ketrol is PBTC, is used in a lot of different applications, industrial applications, for the purpose of scale prevention and maintaining equipment to prevent scale from forming on boilers and different equipment. So this is the carbonate cycle that is going on in a body of water, such as a swimming pool. So there's some reactions going on at the surface with CO2, carbon dioxide, and then in the water, the CO2 can react with the water molecules and form carbonic acid. And then that go. There's these different equilibrium reactions going on. So the carbonic acid can have a H ion added to it, or broken off from it. Sorry, and you'll get the H ion plus bicarbonate, and then that second H can come off and forms just the carbonate, which combines with the calcium. Actually, it combines with it can combine with different metals that are in the water, sodium, magnesium, and gets sort of stored in the water as like calcium carbonate, as like a mineral carbonate dissolved in the water. So what happens when you add either bicarbonate, which is alkalinity, or the carbonate, which would be like the pH up, the soda ash, is, so you add this in the water, it actually takes H ions from the water, which is what causes the pH to go up. So if you're adding a soda ash, it takes two H ions, and if you add a bicarbonate, it only takes one. So the pH doesn't go up as much with the bicarbonate. But these reactions are just going on almost instantaneously. You can, if you want to think about it, like, but just back and forth. So if you add a little bit of this one, then it starts to move in that direction, and comes to and finds the equilibrium. The pH changes a little bit, and so you got some. So at any time, any given time, you have some. Some of each of these things in the water at any time. Okay, so CYA, cyanuric acid. This is used to stabilize chlorine. So you want your CYA level to be between 30 and 50 ppms is what's recommended. In the industry, anything higher than that is not really necessary, and higher than 100 ppms, you start to see problems with the killing power of the chlorine tends to decrease, and you end up having to add, I guess the best estimates are something like, I forget what it is actually, how much chlorine, but you end up having to add more chlorine than you normally would if you have very high CYA levels, such as above 100 ppm. So even like 10, 15 ppm CYA level is good enough to do the job that it's meant to do. So really between 30 and 50 is the most you should aim for. And really the least on the lower end of that if you can. So what the CYA does is it interacts with the chlorine elements, and it protects it from the sunlight, because with no CYA in the water, sunlight will rapidly degrade chlorine in water. So the CYA protects it from the sun, lets it last much longer. It reduces the killing power, but it increases the amount of time that the chlorine lets the chlorine stay in the water for, even in indirect sunlight. So that's the only purpose of the CYA. Before they discovered CYA was a good thing to add to pools, they people with pools, I guess maybe in the 50s, I think they started using sometime after the 60s, or maybe in the 60s or after that, or sometime in the 50s. But before that, people would have to, I guess, add chlorine. I'm told every day, every morning, you would have to go out, add a little bit of chlorine to the pool. And so now with the CYA, most people just add it like once a week in the form of tabs, or however they do, but it stays in the water much longer. So when people talk about stabilized versus unstabilized chlorine, it just means that, so the trichlor, the tabs, and the dichlor, the powder, which is stabilized, they have this molecule, and the dichlor, instead of a H, it has a chlorine. It has two chlorines, right? Dichlor. So there's two chlorines on the dichlor molecule. The trichlor has three chlorines, 1, 2, 3 in each of those spots. So as the trichlor and dichlor are basically a cyanuric acid molecule with chlorines atoms. As a chlorinated cyanuric acid is basically what they are, with those chlorine atoms, on those either 2 or 3 spots on the ring there. So yeah, those are the two main kinds of stabilized chlorine, is the dichlor and trichlor. So unstabilized are other forms of chlorine. So calcium hypochlorite is a calcium with chlorine, and then sodium hypochlorite, which is a liquid, is just sodium and chlorine. So let's see. Someone has a question. I'm seeing. Okay, cool. Someone wrote a question. This is the first question I got so far in these 4 things. With so much CYA coming from use of tablets, what is the best way of maintaining such a low CYA? We regularly see jumps of 30 to 40 ppms in just a month from use of tablets and cal hypo shock. So using cal hypo shock is better than using dichlor, because the dichlor shock will add a lot of CYA if you use that. So cal hypo shock is definitely a good idea. That's one of the things you can do. But really, there's not a whole lot you can do to remove CYA from the water. I mean, if besides draining the pool, you sort of have to, I guess, at the end of each season, if you know what the CYA is, and when you close the pools, then try to decide how much you want to bring it down for the year, and drain your pool that much, drain the pool that much if you can. Because draining is really the only way to get rid of it, besides splashing out of the pool or backwashing, it doesn't really break down. The same thing that makes the cyanuric acid so great at protecting the chlorine and stabilizing it, right? It basically stabilizes it. So it's very stable. It's this ring molecule. Rings tend to be stable, more stable molecules. And so the same thing that protects it from the sun and stabilizes chlorine also makes it, the CYA, very stable in water and hard to break down. There's not really a way to do that. There was two, they showed me two CYA removers that are on the market, and I tested both of them extensively, and I didn't see any positive results with either one of them. So I have yet to see a solution for getting out CYA. I've thought about it. I'm not sure there is really a cost-effective solution, because any way to get it out that would be more complex than something simple, it would just be more cost effective to drain the pool. Or if your CYA is even like 100 at the end of a season, you might want to try to drain half the pool, so at least you start out at a better place. Sorry about that. Get that later. So yeah, I hope that answers your question. It's kind of a tough question. There's not like a great solution to it. Just drain it. Draining, if you need to lower it, you gotta drain water out. That's it. Or reverse osmosis. But I'm not sure how available that is or what the cost would be. But there are like trucks that'll bring a reverse osmosis rig that'll get it out too. It'll get out all the minerals and purify the water too. So I guess that's the only other option I can give you. So okay, if that's it, I hope that helps. So let's see the next slide, if I can get to. So this slide, I wanted to show you something I was talking about before. I think without any CYA, this is the percent chlorine. So you start out at 100% chlorine. Okay, so and then this axis is the number of hours. So 1, 2, 3, 4 hours later. Oh, okay. You just bought a truck that has reverse osmosis. So okay, there you go. That's cool. I wasn't sure how many people actually use that, but hold on a second, man. It's my wife calling. Maybe it's important. Sorry about that. I'll edit this out later. Hello. Hey. Oh, I got that already. Hey, I'm in the middle of something. Can I call you back if it's not emergency? I have it right now, yeah. Okay. All right, cool. Okay, see you. Bye. Okay, yeah, my wife called me this twice, so she said something from the school, but wanted them to their immunization records because just started the school. So that's all right though. I'll get that to him tomorrow. It's fine. Okay, you bought a truck that has, okay, yeah, so that's cool. That should be able to reduce your CYA levels. The reverse osmosis truck. I wonder how many people actually do have trucks that have pool services around. But let's see. Okay, so yeah, so get back to what I was saying. So 0, 1, 2, 3, 4 hours later. So you start at 100% chlorine. The red one, you don't have any CYA in the water. So you start at 100 and the percent chlorine goes down pretty fast. After an hour, it's only at like 20%, 20, 30%. 2 hours, it's down to like 10, 15. And 3, 4 hours, it's almost zero, less than 10% chlorine left. So That's in direct sunlight, I believe. So if you take 25 ppm CYA and between 50 or 100 CYA, you start at 100% chlorine. So for both of these lines are pretty close, like 80-90% after an hour. Well, closer to 80 or 85, I guess. So even closer than that. So after a couple hours, it's still like between like 70-80%. And even you can see the difference between like 25 ppms and 50 to 100. 50 to 100, there's no difference. They're close enough that they grouped them together on that study. So and then the difference between 25 ppms and that is only like what, like 10%. So with the extra CYA, you get a reduced killing power, but you do keep about maybe 10% more, a little bit more. So there is that trade-off there. I think a lot of states regulate the CYA for their public pools to be below 100 ppm. So you have to keep that below 100 ppm. So maybe the person that bought a truck, maybe I'm going to take a guess and say you're servicing some commercial pools in those states that regulate it, and that's why you need that truck. I'm just curious how many residential people actually use that service. Maybe not sure, but for like a commercial pool, if they had to shut down, if their CYA was too high, there's no real way to get it out other than draining. Maybe that is the answer for that. Okay, so CYA levels increase, the kill times also increase with either a little bit or no benefit for stabilization, which is the purpose of the CYA. And the kill times, I was talking about this before, not affected by the pH, at least not significantly, where it's not when CYA is present in the water. So the CYA level, and even more so the level of the free chlorine, those are the predominant factors in determining killing power in the water. I thought this was on water. Okay, so we ended up talking about chlorine anyway, even though this is just about water balance. So it's all related, everything, all these things are connected. So that's sort of how I like to think about the water and the water balance. So having balanced water is like having like a good foundation for a house. It's a good foundation for your pool water. So if you have a good balance, or at least close, all you need to get is close. If all your factors are close to what they should be, you pretty much can get by with no problems. Properly balanced water, it'll prevent all kinds of problems, from sanitation problems, and then scaling problems, or serious corrosion problems, corrosion of metal parts, heaters, or even corroding, etching plaster, or vinyl, especially new plaster, is really important when you get a new plaster job. The first few days, the first month, the first few months, it's really important to keep an eye on your water chemistry, test it a lot if you're, and follow the guidelines for that, for the new plaster for a startup. But even for like a new pool, I always like to keep a close eye on the water chemistry, test it first, see what it looks like, and test it every day if you can, and then you can get a feeling after you work on it for a few weeks, and then you start to get a feeling for how the water behaves, and if it's plaster, and how the reactions in the water are causing different changes. You get a feeling for how the water behaves and what you need to do. You don't have to test as often, at least maybe once a week. It's probably what most people like to test it, just once a week. But especially with like a new body of water, like keep a close eye on it at first, and you'll get a feeling for the chemistry. So proper water balance also makes the water more comfortable to swim. If the pH and everything is right, it creates the optimal conditions. People have been swimming in this country since the 60s and 70s, I think, is when the industry really exploded, besides just a few like custom pools, in the 50s and before that. I know they had pools, but it really exploded after the 60s into the 70s with residential pools. So that's, at least over 50 years people have been doing this. So this is the combination that works, the control on the pH, the alkalinity, and the hardness, and these other factors that we know about that helps maintain your pool and make it comfortable and fun to swim in and safe to swim. So one other thing, it's sort of on the outskirts of these factors I like to look at, is called total dissolved solids, TDS. The best, you can measure it by if you had a good enough balance, you could take a water sample, weigh it, and evaporate the water, and then determine the weight of the solids left behind. Because what it is just any solids that are dissolved into the water. But the most practical way to measure it is with a TDS pen, which you can also infer the salt measurement from for salt pools. And it's basically, it looks like a pH pen. So they have pens that measure pH and TDS, which are more expensive. But you can also get a pen that measures just TDS. So it'll measure the total dissolved solids. It'll measure the salt, which is just a conversion of the same measurement. And it measures the conductivity of the water, which is actually how it works. Is it has two electrodes on the pen, which measures conductivity in the water, because the more solids are dissolved in the water, the more conductive it is. So it does an internal calculation from conductivity, can estimate the amount of solids in parts per thousand or parts per million. So that's one of the tools that I use, and some of you guys probably use it too. TDS should be pretty low. Most pools it's below like 500. Any higher, if it's higher than like 1500, that could indicate a problem where the water just needs to be drained, like hasn't been drained for a really long time, but usually when it gets that high, I see other problems too, like really high CYA levels. So I don't see too many with like that high of a TDS. The exception being salt pools, because the number is however much salt you add, you have to subtract that, because you actually want that salt in the water. So it could be 3,000, 3,500 ppms higher, because that's how much salt is in the water. So TDS is another thing. You only really can lower it by draining in general. Depends what compounds they are, because it's sort of a general measurement. But if it's really high, the best way to lower the level is by draining. But like I said, usually there's other problems like high CYA that they probably need to be addressed anyway if it's that high. It's still good to measure that. Just another thing to look at to give you an idea of what's going on in your water. Excuse me. So let me get a sip of water here. So also any minerals in the water besides calcium. Calcium's supposed to be there, but like copper, silver, iron, there's not really any benefits for these minerals. They should be zero in your pool water. The copper and iron obviously can cause stains. Silver can cause black stains. Copper is usually greenish color. Iron is like a brown rust color. Now the benefits for some of these are like copper and silver make really good algicides. So there's a trade-off there if you use copper algicide, but then you end up with a copper level in your water that can't really be removed other than by draining. Who would have thought? Yeah, the metals are not that easy to remove from water. Sometimes iron's probably the easiest one to remove. You can precipitate it out at a high pH above like 8. It'll start to precipitate out. The cause of iron can be natural, could be from metal plumbing or from a well. It can occur naturally in wells. It also could be from corrosion. If you see rust in the pool, it's probably from that. Um, and then copper and silver copper is usually from plumbing because it's used in plumbing. Also on like heaters, pool heaters, the heat exchangers are made of copper and copper-based algicides. So those are the three main sources copper enters your water. So silver, some pool products use silver. It's also a really good algicide sanitizer. Some pool products do contain silver. But with any of these, the trade-off is they do work really good, but they don't leave the water very easily and can cause stains. So you can use them if you want to. It depends, what every pool, every situation is a little different, but try not to overdose any algicides that have copper in them, because if you overdose them, then you're just increasing the likelihood that it'll stain, But when they're used according to the directions, they can be used without having any staining problems. Also, like with the copper algicides, I know our formulations they contain sequestering. When they're formulated, they are formulated with a way that sequesters them. So I guess some lower quality copper products might just contain the copper without the sequestering part of the formula, and they would have a much higher chance to stain than the ones that are formulated with it already in the formula. The Ketrol Plus, you can use that if you're worried about staining. Again, that's a great product for preventing stains. Calcium scale, but also any kind of metals. Calcium's a metal, copper's a metal, silver's a metal, iron's a metal. So it'll help. It binds to it binds to all these metals. Is really great at preventing any kind of staining. And then we do have stain removal procedure that I talked about in the last one. So if you do get stains, there's a way to approach that too. Depends on how long the stain's there and what kind of stain it is, but you can have really good results even if you do have stains. It is possible to remove them with a little bit of time and effort. So this is the Langelier saturation index calculation that I talked about earlier. So I understand people don't do this calculation every time they balance the water. Sometimes it's better just to keep it simple. Like Ed Brown always told me, like, KISS. He said, "Keep it simple, stupid." So yeah, sometimes that's the best way, just to keep it simple and go for targets: 200 calcium, 100 alkalinity, 7.5 pH, nice and easy. But once in a while, it's good to do LSI calculation to see where your water really stands on this index. So the way that it works is if you get a value of 0, that means your water is perfectly balanced, right? So that's pretty hard to get exactly at 0. I don't expect you to do that. But I would recommend keeping it on the higher side of this index, because scaling is much easier of a problem to fix later than corrosion. So it is recommended to keep it slightly higher, especially before you winterize. It's good to keep it on the higher end, because the temperature you can see the temperature factor is part of this calculation, and the lower the temperature, the more corrosive your water is. So if you think about that, in the winter, the temperature drops a lot. It's going to bring this index way down. It's good to start off a little bit higher, on the higher side. And in general, just for normally, it's good to keep it a little bit higher. If you probably can't keep it exactly on 0, I would aim for a little bit higher, you know. So for pools, they say anywhere between minus 0.3 and plus 0.3 is okay. So they don't expect you to keep it exactly at 0. Anywhere between here, and you should not really have any problems related to corrosion or scaling. Okay, so the saturation index, the way that you get this number is you add these things together. So pH is just, so let's just use a target example. So for a pool that's balanced by target, so let's say the pH is 7.5, so 7.5, and then we go to the temperature factor. So let's just say like 80 degrees. Let's see, I have it on the next page. Okay, so we have to, all right, I'll go back. So we have to look up the temperature factor for 80 degrees. It's like, okay, let's say 76 is 0.6. Okay, so plus 0.6. Okay, so then the next thing, calcium factor, right? So we go look up the calcium. So the calcium should be 200 ppm. So 200 is, let's see, 1.9. So plus 1.9, right? Okay. So alkalinity is next. Okay, so we go to alkalinity, it's 100. Okay, 100 alkalinity is a factor of 2. So then plus 2. Okay, and then minus the TDS factor, which is okay. So let's say it's less than 1,000 ppm, 12.1. So then I minus 12.1, and result is minus 0.1. Okay, so with the perfectly balanced to 7.5, 100 alkalinity, 200 calcium, you get a minus 0.1 on this index. So it's a little bit on the corrosive side. So, yeah, it's good to keep it a little bit on the higher side, but minus 0.1 is still within that range, still pretty close to 0. So I think that's fine. I think that's just fine. And you can play with different numbers and see how they affect the equation, but yeah, okay. So this chart is just showing your pH is optimal for pool water. Alkalinity buffers against the pH dropping. Calcium. So on a newly plastered pool, you're going to use some of the calcium in the water might actually diffuse into the plaster. So you want to keep it higher and the alkalinity higher as well, so you don't end up leaching calcium from the plaster, like we were talking about before. Let's see. So CYA. Okay, I just wrote 50 as a target, but between 30 and 50 is good. Above 100 should be lowered. So TDS for salt pools, add about 3,500 or subtract about 3,500, or depending on how you're looking at it. And then minerals, you just want to keep copper, any silver, any minerals, keep those levels as low as you can. Like I said, they're good algicides, but they you don't need them in the water for any other reason. Right. So I hope you guys got some good information and a little bit different perspective maybe than you're used to. If you have any questions, you can contact me. I'm Rein, the chemist here. So I look forward to hearing from you and helping you with whatever I can, whatever I can do for you. Let me know. I'll try to